All right. Good afternoon, good morning, good evening from wherever you are. We are here at the Urban Economic Forum. This is the fifth edition, and the International Society of Cities and Regional Planners virtual pre-Congress. We've got 𝐒𝐞𝐬𝐬𝐢𝐨𝐵 here with this special session on reconsidering the value of underground spaces in a sustainable and climate responsive urban future. We have three very important and distinguished presenters today, and I will very shortly be running through their bios as an introduction before they present. But before that, if there are any questions, please ensure to put the questions in the chat box. We would collate the questions in the course of the presentation, and we would address all the questions at the end of the third presentation. I'm pretty sure everyone is as excited as myself, and I would like to introduce the very first presenter, Dr. Shana Debrock. She's an urban designer, a researcher with the Flemish Policy Office since 2014. Shana has worked at the Department of Environment and Spatial Development as a policy officer for the urban development and system innovation. She is responsible for drawing up policy proposals with regards to urban underground planning. In addition, our fascination with the subsurface led to an ongoing doctoral research with the University of Antwerp on underground urbanism and the way in which the subsurface can be integrated in planning, in policy, and in design. During her trajectory, she has had the opportunity to work with the liaison officer as a liaison officer and studio consultant with the Harvard University Graduate School. Please join me as we make welcome Dr. Shana Debrock as she gives her presentation. Thank you.
Hi, I'll share my screen. Thank you for the introduction. Although I must say, I'm not a doctor yet, still have some papers to write, but slow but steady. Okay, so I'll share my screen. Okay, it's visible, I suppose. Okay. So, good afternoon. I'm Shana Debrock, and I would like to talk about the efforts we're making in the Flanders concerning underground planning tools to increase urban sustainability. But first, let me provide you with some urban planning context. So Flanders faces many challenges. 33% of the surface is considered settlement area and 14% of its surface is effective soil sealed area. This is amongst the highest in Europe. And also every day, an average of 6 hectares a day of land take is taking place. So this leads to, amongst other things, heat stress, flooding, and puts a lot of pressure on the open space. So that's why Flemish planning policy intends to bring down urban sprawl to a standstill by lowering our daily land take from 6 today to 0 hectares by 2040. We're doing that by means of applying densification development strategies and focusing on nodal development. However, we have seen that the subsurface is missing in this whole story. So in order to bridge the gap between surface and subsurface policy, we instigated a policy exploration to examine if efficient use of the urban underground space could be a viable solution for lowering our daily land take and fulfilling our Flemish policy objectives on spatial efficiency. So how do we define urban underground space? Because there are lots and lots of definitions. We define urban underground space as man-made built underground spaces for people to wander, to reside, amongst other things, and they can be used for a very broad range of functions. So we mean to look beyond utilities, technical facilities, and storage, and so on. However, today we see that the subsurface, and this is a trend that's going on worldwide, not just in Flanders, is often characterized by great diversity in technical functions, but also increasing claims conflicting functions and competition. So underground developments are planned in an ad hoc, from a last resort, first come, first serve practice. And sectors seem to be working side by side without regard for common interest. So all this is coupled with a lack of knowledge about the location of existing underground structures. You can imagine it leads to a whole bunch of calamities. So there's this certain form of chaos and disorder due to the various space claims that are dealt with without an integrating framework. And this leads to missed opportunities and often financial hangovers. However, we do see that the underground urban space holds several benefits for Flanders. It can contribute to sustainable development goals, to societal and environmental challenges. It can increase urban densities, provide sustainable synergies, enhance quality of life, improve territorial identity, serve as an economic catalyst. But why are most underground spaces still looking like this? So today, however, most of the urban underground spaces are not taking advantage of the potential value that the subsurface holds. Usually, this is what people associate with the subsurface: dark, isolated, rather creepy. And while places that do take advantage of the subsurface can actually look like this. So you can see that we still have a lot of work cut out for us in the transition to sustainable underground spaces in Flanders. But in order to do so, we need to understand the relationship between sustainability and urban underground space, which is a very complex one. And different researchers and policymakers, they also hold up different points of view on this relationship. But to put it bluntly, we see a very strong relationship between sustainable cities and underground as a system of services, and underground space use as one of those systems, as one of those services. We recognize the fact that urban underground space can only contribute to sustainable cities if the subsurface is dealt with in a holistic manner, where all the interactions between the different services are recognized, and the usage of one of those services is also done in a sustainable manner. So if you're going to work in the subsurface, create spaces, it also needs to be done in a sustainable manner. So further on, recently the Flemish government in its entirety has issued a new project, the Flemish Strategy on Sustainable Development. It's an overarching policy project that engages the entire Flemish government and administration. This Flemish strategy holds 7 transition priorities because it's focused on this transition to a more sustainable future. And one of these priorities has a project that focuses on sustainable urban underground spaces. So that's a project that I'm leading. And it actually holds several tools. And first one, and actually I believe one of the most important ones, is that everything depends on the availability of data on the subsurface. Flanders already has an excellent database and knowledge center that gathers and displays data on the subsurface. But from an urban planning point of view, we are actually most interested in how we can use that data, that roughly geological data, how we can use it for planning or executing or designing these underground structures. And we realize that there's actually a great need for translation of this geological data to information for urban planners and designers. Turns out, most of the time, we actually barely understand each other, geologists versus urban planners. So currently, our DOV, that's a database, holds several interesting tools, such as Subsurface 3D Model, a tool that allows you to virtually drill in the subsurface and receive the geological information. And you can also draw a virtual profile. So in addition, we also created a voxel model of Antwerp, and this viewer enables geological, hydrogeological, geotechnical prospection and inclusion of subsurface data in geothermal projects, and also in temporary dewatering, reuse of excavated soil, stability studies, and so on. Another interesting tool are the opportunity maps. This is work in progress, is not done yet. Urban planners, geologists, geographers, and policymakers in Flanders are all working together to develop a framework on the different surface and subsurface parameters to consider when promoting urban underground space. These parameters include spatial context, settlement risk, raw material potential, geological potential, and risk. So all these different multiple dimensions are combined in a map and converted. And the aim is to give straightforward information on the potential of using this urban underground space in different areas in Flanders. We're also working on a planning framework for sustainable urban underground space use. These are considerations when using the subsurface. Like I just said, the subsurface is a system of different surfaces. So this is actually how we're planning to grasp the interrelations and synergies between these surfaces. This is a very difficult one. We're not yet far on it, but this is actually our plan. Also last year, we finalized a research by design project, which involved several local authorities in the Netherlands and Flanders, design agencies, a university, and a knowledge center. So the study, we published it also, is called Designing from the Cross-Section, the Subsurface as a Building Block for the Future-Proof City. So the aim of the design study was to research and redesign strategic urban locations where social challenges required redevelopment of this place. But we had to make sure that they paid explicit attention to the subsurface. So local authorities were asked to come forward with possible case studies. And then each case study, you can see them here, was actually provided with a professional design team and a student design team of the Technical University of Delft. So during this design study, significant importance, like I already mentioned, was attached to the subsurface. And every case study was subjected to a technical session in which the subsurface was analyzed by means of this SEAS methodology. This is created by 𝐒𝐞𝐬𝐬𝐢𝐨𝐵 and Maring, and it's actually a system overview of how the natural and human systems are intertwined and how this is making the surface and the subsurface as one united space. So I will not get into detail, but these are some of the designs that were produced during the design study. And some illustrate a more systemic point of view, and then others focus more on cross sections or even technical profiles. So they had very different outcomes. Okay, then on to the next tool. We also developed a design toolbox for sustainable urban underground spaces. This is based on recent research on design recommendations for sustainable urban underground spaces. This paper has just recently been published last month, I think. And these are actually recommendations that were synthesized in an integrative and holistic manner. So we actually took elements from other disciplines into account and reinterpreted them from an urban design point of view. So these findings, they suggested design recommendations on livability, connectivity, temporality, and interdependency, each with their own set of recommendations. And each sub-recommendation is also attached to a good practice in which this sub-recommendation was done in a proper way. More information can be found on the paper. Also, finally, we're still developing a policy guide for urban underground planning, which is aimed at local authorities and early adopters. This actually includes most of the previously mentioned tools, and we wanted to offer a practical way in which cities can plan their subsurface. So finally, we've arrived at our end game. What we're actually trying to do is develop a coherent, scientifically sound planning policy for sustainable urban underground space use. We're even trying to make a smooth transition to 3D planning, where we also take account of the use of our airspace, not outer space, but our roofs and the impacts of drones and sky bridges. So thank you very much. I hope you found this an interesting presentation on what we're trying to do in Flanders to achieve sustainable urban underground space use.
Awesome. Thank you very much, Shana Debrock, for that very fascinating and insightful presentation. I must really say that's very audacious project there. And one of the key things I've taken from that is the design toolbox. As simple as it is, highlighting 4 key components that would serve as filters. So obviously you mentioned the livability, connectivity, interdependency, and temporality. And I'm sure a lot of cities will benefit greatly from this particular work that you have done. Thank you very much for that. I encourage, if there's any questions, please put them in the chat box. And whilst we go on, we're doing that, I would move on now to our second presenter for this session, and that is Dr. Michael Doyle. He's an assistant professor at the Université Laval School of Architecture in Quebec City of Canada. His current research revolves around the use of artificial intelligence for interacting with large corpuses of text and geo-referenced data. In 2023, he launched a new project that uses machine learning algorithms to characterize urban streets with big data. The funding provided by the FRQSC over the course of 3 years will help produce the prototype for a web-based application that can hopefully be expanded to a planetary scale. Michael Doyle holds a PhD from the EPFL in Switzerland, where he completed his dissertation as a member of the Deep City Project. Join me again as we make welcome Michael Doyle as he gives his presentation.
Thank you very much. So what I'd like to talk about very briefly is the project that I was working on during my dissertation at the EPFL in Switzerland, and then bridge it with a new project that I launched this summer. So the Deep City project, kind of the main impetus for it was to kind of inverse the tendency to go in a planning setting from needs to resources. So we wanted to reverse that and think, how could we think what the underground resource potentials were before we started to think about particular projects or developing planning scenarios. The important thing I'd say also about the Deep City project was that we were trying to think in terms of multi-use. So not just in terms of urban functionality, in terms of space, but also of the other resources that are available and the synergies and conflicts between them. So for instance, of course, buildable space, but also groundwater, geothermal energy, either for heating or cooling, and also geomaterials, that is the things that when excavated could be reused either locally on site or could be transported somewhere else and nearby and to be able to be reused. So we very much looked at I mean, I talk in the way that I like to think about this topic as an n-dimensional city, because for me, it's not about saying, okay, it's either the surface or the underground, but really it's kind of almost a volumetric way of thinking about the city. So which constitutes a lot of things that we don't see. So looking at not only a question of development, but also of preservation. So in Switzerland, for instance, the idea was that we wanted to try to keep a certain characteristic of Swiss cities, which tend to be very small, relatively compact for in many cases. And we wanted to be able to densify them without just building towers everywhere. So the underground became kind of an alternative way to think about that. And the Deep City project had a couple of outputs. So to start from the bottom, we did a spatial econometric analysis of surface and subsurface multi-level spaces. I did this on the city of Montreal, which has a kind of extensive underground surface, urban commercial and cultural space. We did cost energy simulations of a commercial underground project. And one of my colleagues in civil engineering developed a matrix of interactions between the resources to try to figure out, okay, what could be potential benefits and disadvantages of using underground water, for instance, in the same location we're trying to do geothermal. And also, and what I want to talk about today, which I focused on significantly in my PhD, was the development of an investigative mapping method. So the mapping method, the idea was not that we would say, not that we would take in a large urban area and say, okay, here's what you need to do with your underground, because there obviously with planning, there are many things that are extremely complex and we wouldn't presume to kind of master all of those things. But what we wanted to be able to try to do was to somehow find a way to summarize and get on the table for an eventual planning setting some of the opportunities and risk, or areas of opportunity and risk that could present themselves when we're looking at either the types of the qualities of the ground material, its potential for geothermal energy, where there is groundwater, and whether that groundwater tends to be used for drinking water, if it tends to also be a source of potential flooding during rainy seasons, which was the case here in Dakar, and then also built space. So, and when we look at the potential of built space, we tended, this was the position we took, to look at ground that was relatively stable. So not necessarily ground that is easy to excavate and could be and would require a significant amount of construction to stabilize it. So, I mean, I understand that that's a decision that can be made to decide how you approach the buildability of the ground. So we did this typically in collaboration with local actors, planners, geologists, and we tried to get an understanding from kind of the tacit knowledge of what people had locally about how you could work with certain geomaterials and what the challenges were related to those. We also added something which I kind of brought to the table as someone trained in architecture and urban planning. The project hadn't looked at all on what the actual characteristics of the urban surface morphology were, and I wanted to bring that in as a kind of extra point, because what we realized, particularly looking at Montreal as an example, was that you tend to have the potential for densification often tends to be in places that are already relatively central, because they afford a kind of easy connectivity. There tends to be lots of people passing. That's for, of course, mostly commercial activities or cultural activities in certain cities. But centrality was also something we wanted to look at, because in places that are not very central for accessibility to people, that can be advantageous sometimes for other types of infrastructures that you want to put underground and that you don't expect a large number of people to be frequenting regularly. So the idea was that we tried to test out was, okay, if we combine these potentials together in a single map at a particular depth, so here we have 0 to 15 meters deep, what does that tell us? So what we realized was that, and it's not necessarily, because I compare now with what Shana, you were showing us, it's not an opportunity map per se, because what is sort of the reddish color there is actually the areas where there is a large overlap of the potentials for all the 4 resources. And therefore, it's an area that if we were to develop either surface or underground, it becomes a place where we say, okay, there's a variety of things going on. There are some questions that need to be raised, and maybe an interdisciplinary team that needs to be composed to start to investigate questions, say, okay, what are the risks and advantages in this particular area? So it's more kind of like zones where what's at stake is kind of different. And so the stakes here are being combined. So the disadvantage of that was that in combining all of that, the nuances start to disappear. We kind of can't work with many, many layers of data. There's a lot of summarizing, a lot of dimensionality reduction that's required. And so what I saw this as was a kind of small data scenario. So what that had me kind of pushed me to do in a postdoc, which I picked up after my dissertation, was how to use machine learning and artificial intelligence in order to try to index ground potentials using a large quantity of data that characterized the underground. And this is a test that I did for the city of the canton of Geneva in Switzerland. And so the idea was that we would let the self-organizing model propose to us areas of multiple resource combinations and in an order of similarity. So from the red to the blue is the most different to is an order of similarity. And what you see with the traces there of the nodes is a neural network, and a one-dimensional neural network that is connecting some of the typical cases and putting them in order of similarity. So you could follow this line, you could follow the neural network around and say, okay, from the water areas to the highly sort of bedrock mountainous areas, there are things going on that the algorithm is telling us that we could investigate and find out more about. So the postdoc was a relatively short exercise, and I had to career-wise, had to put that to a side once I got a professor position here in Canada. But I'm now launching a new project, which allows me to come back to some of the things I was working on with Deep City and also now with machine learning, as I also personally get better at programming and understanding how these things work. So this project, which I've called Masks of the Genius Loci, a prototype for an instrument for deciphering street identity with big data and machine learning algorithms, is looking at how to capture the singularity of an urban street. So what makes one street different or similar to all other streets? So the street becomes kind of a common denominator. The objective of the project is to build a prototype for a computational instrument that will help us see what makes one street not like every other street. That's how we're thinking of identity. And hopefully, well, not hopefully, but it actually will be unique as far as I've been able to find with this kind of work in incorporating geological and hydrogeological data, which we have a pretty good availability of in the province of Quebec, but I'd like to eventually expand this beyond just the province of Quebec. So that will depend on the kind of data and how it's represented beyond in other contexts. So just to give kind of an idea then of how we will combine this type of data together. So first of all, with what I mean when I say AI is I mean machine learning algorithms, and specifically the self-organizing map and high dimensional data sets. So basically data sets that we compose that have lots and lots of data, lots of characteristics and features, and that we can layer on top of each other, and it become basically impractical for an individual human being to try to sort out. So we let the machine or the algorithms kind of sort that out for us, and then we investigate what it's learned. So what it will do is we'll create a vector of numbers for each street that represent its similarities to other streets. So on a variety of features. So we have the topological and geometrical features, points of interest that we get from OpenStreetMap, vegetalization and mineralization features based on satellite data, geological features based on the geological survey here in the province, topographical features based on elevation, elevation data, etc. So the idea is to have as much of this as possible, because then we can always tune it and say we want to look specifically at this, we want to look specifically at that, but the identity, the kind of numerical identity we give to the street always allows us to kind of give it a unique identifier in a way. So it has some advantages in that the missing data can be guessed by the model. So that's something I'd like to explore, is the opportunity to say, we think that the ground is like this here, but we're not really sure. We should probably check. And we could also then take this long vector and reduce it to one number and situate each street relative to all of the streets as an individual within a group. And that's basically, technically speaking, using the self-organizing map as a one-dimensional encoder. So the next step on this project are to continue to work on this prototype, adding features, improving also the computational techniques. In next year, I hope, or 2024-2025 academic year, I hope to build a web application that allows us to interact with the AI model so it can start being tested. And then in 2025-2026, I want to explore some use scenarios with students in architectural urban design studios, because as a professor in a school like that, it's typical that we kind of bring our research into the classroom and kind of explore opportunities. So there's a website for the project, which will soon have more information in English. It's currently in French. And hopefully if the slides can be shared with you, you'll have access to that. And also here are a couple references to some of the work that I mentioned in my talk. So thank you very much.
Thank you very much, Dr. Michael, for that really very inspiring and very insightful presentation as well. And that's the interesting thing about the underground is I've been I've been involved in quite a lot of seminars, and we can see the multifaceted perspectives that the underground basically presents to us. I'm really particularly very I was impressed by the your project, which I'll be looking forward and be following. And it basically resonates with some of the things that we are also looking at, from the context, even from a developing world context. The underground spaces have different contexts in different regions, and there's their commonalities. I remember recently an admiral was speaking, and he said, perhaps we should not now just think outside of the box, but we should start thinking without the box. So the concept of the n-dimensional city is really very, very interesting. Thank you very much once again for that. Let's get our questions going, and that leads us really nicely to our very last presenter, and that is Dr. Asal Bidarmaghz. And she is a senior lecturer in geotechnical engineering at the School of Civil Engineering and Environmental Engineering at the University of South Wales in Sydney. Her research expertise lies in energy geotechnics and energy geostructures. Asal received a PhD in civil engineering, that is in geothermal technologies, from the University of Melbourne in 2015. Following her doctorate, she worked as a postdoctoral research fellow at the Department of Infrastructure Engineering, University of Melbourne from 2015 to 2017. She then went on to work as a research associate at the Engineering Department at the University of Cambridge from 2017 to 2019, before then joining University of UNSW in 2019 as a lecturer. Asal research activities are focused on geoenergy systems with a particular emphasis on hydrothermal mechanical characteristics of urban subsurface and underground structures. Our research involves large-scale simulation of urban underground climate change and the quantification of its consequent geotechnical, environmental and hydrological impacts. By improving the sustainability of underground spaces and resources, Asal's research contributes significantly to the field and drives progress in optimizing our usage of these valuable assets. Once again, with a warm welcome, let's get Asal to start our presentation. Thank you very much.
Thank you very much for the introduction. Can you see my presentation? Perfect. So my talk is about how we can use underground space and structures and energy resources in a sustainable and resilient manner, very much aligned with what we already heard from Shana and Michael, slightly different from the engineering point of view. So when we talk about urban heat island effect, all of you, most of you, if not all of you, is familiar with that concept. And also the fact that we feel urban heat island when that's how we feel it, is that we just like higher temperatures in the cities, also very high temperatures at the surface. So this at the right hand side is a surface of a playground in the west side of Sydney that reached 85 degrees Celsius in summertime. However, most of the time we ignore what is happening in the urban subsurface. So very similar to the climate change and urban heat island effect above surface, the phenomenon, as we call it, underground climate change, is also happening in the shallow subsurface. And some of the evidence could be, as for example, the London Tube high temperatures that some stations experience, 42 degrees C has been reported for them. Or even here in Sydney, we have measured more than around 25 meter below ground level temperature, soil temperature of 38 degrees C. So it's very difficult, and it's basically impossible to ignore and close our eyes on what is happening in the underground. And why this is happening, it's basically a majority or a big part of it is because of the increased activities in urban underground, human activities, anthropogenic heat fluxes, like the large number of tunnels and constructions and developments that we are doing in the urban underground. Like in Sydney, for example, we have kilometers of tunnels for the next 20 years to be constructed, and multi-level car parks, basements, high voltage cables, and you name it. And also another factor is that the exchange of heat between the above surface and underground. So this is rules of physics, that there's no way we can stop it. And depending on the temperature difference, the heat will be exchanged between above and underground. So this is what we call subsurface urban heat island. It's rather new topic, and there are very limited number of researchers around the world working on this, but it's actually getting more attention day by day, and which has caused what we call urban underground climate change. So what it means is that most cities, most major cities or densely populated cities, are suffering from a significantly warmer than normal subsurface. And when we talk about subsurface, I'm talking about maximum 100 meters below surface, or even 50. What are the impacts? These are impacting the subsurface sustainability and serviceability. And this contradicts the idea that we want to utilize urban underground in a sustainable manner for the future, for the future generation. Because these high temperatures is some of the impacts I have listed here. It will affect the above and underground structural instability, like tunnels, like retaining walls or piles, any structural element that has, due to these high temperatures, will actually, its stability will be impacted. Groundwater quality and quantity. Groundwater temperature is one of the main things that has been measured in many cities around the world that actually is an indication of underground climate change. Underground ventilation, air conditioning inefficiency. So if you have stepped into London Tube or any, like in New York or in Singapore, you can feel that heat in underground space, in the platform, in the trains. And this is because the soil surrounding those tunnels is significantly warmer than it is supposed to be. So it is excuse me, it's thermally saturated. It cannot absorb any more heat. Not to mention the thermal discomfort for passengers, the health issues for the workers in urban underground. So if you're really thinking or moving towards using urban underground in a sustainable way, we have to pay attention to its climate as well. So those were observations and measurements in the field. However, my research in the past few years has been mainly focused on quantification of temperature increase in some areas. For example, this one is in Kensington and Chelsea in London. Kensington and Chelsea is a densely populated borough with tens of thousands of residential basements and tens of kilometers of train lines underneath. So basements and train lines, they are main contributors to underground temperature increase. So what we observed through numerical modeling was that the maximum 5 to 8 degrees Celsius temperature increase was observed in part of the subsurface. And if we actually take the average temperature, the volume average temperature increase in that borough, which has got 12 kilometers square surface area, this could fulfill up to 75% of total energy demand or gas demand of that borough. That could also be translated into around 33% savings in CO2 emissions. So this heat exists right underneath us, and we can use it. Another study that I was involved with was the same research, but in Cardiff, Wales. So Cardiff also has got a large number of residential basements, not as busy as Kensington, Chelsea. So what we observed was average of 2 to 3 degrees C temperature increase in the subsurface. And if we translate that to energy and thermal energy, up to 100%, depending on the usage and also the household type of the energy demand could be supplied, and up to 75% saving into the CO2 emissions, as opposed to using electricity or fossil fuels. There are similar research around the world, for example, in the US, Chicago, several German cities, in Japan, and many more that are quantifying the temperature increase in the subsurface and then translating it into geothermal potential. And we're talking about shallow geothermal energy. So what can we potentially do? Because this exists, underground climate change exists in our view, in my view, but can we change it into opportunities? Yes, we can. So this is like we have a massive amount of heating energy. So what we can do is we just by some planning, we can extract that heat and use it in winter time. We can actually extract it from the shallow subsurface, transfer it to your building, and heat up your house. So once you do that, you will increase the capacity in the ground to also reject some heat. But that which means that not only you can use it for heating, but also you will create capacity for cooling. So it is a heating and cooling potential. Because if you continuously extract that heat, then you're going to freeze the ground, and that's not what we want. If you continuously reject the heat, you're going to actually make the ground very, very warm. And that's also not what we want. So it must be a balance. And that's the perfect balance. We have to first take it out and then have that balance with heating and cooling. So the most conventional way of extracting or exchanging heat with shallow subsurface between spaces above or underground and the ground are borehole heat exchangers that are essentially high density polyethylene pipes, closed loop with water circulating within, embedded in a borehole that in summertime they take the heat from the building and reject it to the surrounding ground as it has a lower temperature, and in winter time the process is vice versa. However, the high capital cost like drilling, in particular installation of these borehole heat exchangers, has hindered its wide application. So the new trend for exchanging heat or extracting and rejecting geothermal energy is called energy geostructures, which means that any structure which has contact with the ground, with tunnel, piles, walls, slab, pavements, can be converted into energy geostructures. So, for example, we can embed the pipes in the lining of a tunnel, and to take the heat from not only the tunnel area, which is actually elevated in temperature, but also from the surrounding soil, and then transfer them to the building above ground. And once we create that capacity, then we can take the heat from the building above the ground and reject it to the ground in the hot season. And also energy piles. So any high rise, any tall building requires piles, regardless of the energy supply or not. So the installation, the drilling, everything is there and it has to be covered. So what if we actually add some pipes in there so we can exchange heat as well? So it's a dual purpose thing, structural and thermal. This is the energy geostructures also rather new in the world. So we have some pilot projects, for example, energy piles in University of Melbourne, diaphragm walls in Vienna, and energy tunnels, just small segments in Stuttgart. And as you see, these are the rebars for the energy for the piles, and the high density polyethylene pipes are cable tied to the rebars, and water would be circulating within, and then this will be pushed into the ground. So based on the research and estimations that we've done, a kilometer long of an energy tunnel can supply heating and cooling demand of around 100 apartments if you're thinking of a typical household. So if I want to put this in the context of New South Wales, Sydney, where I'm living and working, and talking about the benefits of this shallow subsurface energy, or what if we change the underground climate change into opportunities in terms of energy. For example, if we switch heating and cooling of a typical school in Sydney from electricity or fossil fuel to geothermal energy, that school will save around 110,000 Australian dollar per year. This can be around saving of more than 600 tons of CO2 emission per year for a typical school. And we have around 3,000 plus schools in Sydney. And if we look into the climate related death rate, if we switch all those schools, 3,000 plus schools, to geothermal, we will have 440 fewer climate related deaths per year. And this is a massive number. And so other benefits I can point out to is that you can have concurrent heating and cooling, but you can actually heat up the pool once you are cooling down the gym next door. So the ground does have the capacity to provide heating and cooling concurrently if it is designed perfectly. And so it's perfect for spaces with high energy demand, schools, hospitals, shopping centers, the big consumers. And it is proven that effectively controls shallow subsurface thermal balance. So if we want to bring the balance to the thermal balance to the subsurface to guarantee the stability of structures, the groundwater quality and quantity, the ventilation efficiency of underground spaces, we have to bring that balance back and using shallow geothermal systems is one of the most important, one of the major ways. And it will improve stability and serviceability of underground infrastructures. Just imagine that the tunnel that we construct today in 150 years' time might be too hot to use. So we have to think of retrofits for ventilations, which is costly and most of the time not very sustainable. So underground climate needs to be considered in the design process of underground structures. Again, just to finish my talk, I want to highlight or point out to how much we will save if all schools in New South Wales switch to geothermal. We're talking about more than $340 million per year are energy consumption savings, and around 2 million tons of CO2 emission savings per year, and also 400 or more fewer climate-related deaths if we switch to a sustainable, renewable source of energy that exists right underneath us. Yep. Thank you very much.
Awesome. Thank you very much, Dr. Asal, for that very interesting presentation as well. Really, I have been really very impressed by the quality, and not just that, the different perspectives that we've basically addressed in our different presentations. Obviously, this has a different twist to the other two presentations, where this basically just opened up an entire frontier on underground climate change, which is something we're usually not it's usually not a topic of discussion. But the most important thing that I've been able to draw from this are the opportunities therein that you've basically highlighted, that that basically requires a little bit more thinking in terms of from decision makers, from professionals in different cities, as to opportunities and benefits for our cities, not just from an environmental point of view, but from a social and economic perspective as well. So thank you very much, Dr. Asal, for that presentation. And I know we're running we're running out of time, but we have two questions, and those questions have come from Shana, and I presume these questions, I do have a question as well, and it's a general question. So I'll read the first one. It says, will it be possible for to reinterpret the outcome of characterization of urban streets to design recommendations, since you probably will be able to deduce the parameters of good practices within the unique characteristics of each place? So I'm assuming this is for Dr. Michael Doyle.
Yes. Yeah, thanks for the question. I haven't really thought of it that way, but I think you definitely could use it to deduce parameters of good practices. Basically, what you would have to have is a kind of series of model streets. You would say, we know things have worked well here, so what other streets are like those streets? And then, of course, for me, there would be an initial kind of validation where you would say, okay, does that seem to be, is the good practice something that the algorithm has seen indirectly, and that we can say, okay, yes, that practice could also work somewhere else. So does it allow for the transposability from one street segment to another? That's something that definitely I'm keeping in mind to explore. Because actually, if it doesn't, then something could be missing. Either it's tacit knowledge that we have that we know something the machine can't see, or we say, there's an aspect that we haven't been able to capture. Is there a way we could capture that aspect?
Thank you.
Thank you for the question. I could actually answer the other one that precedes this one, the urban streets. It was, I think, because urban streets are more, there are more urban streets than urban plazas. I think that's and because the basic departure point for the data source is OpenStreetMap. I wanted something that was open source, something free that would be easy to get on a planetary scale eventually. And so basically the download, the robot is crawling the properties of street segments in OpenStreetMap. So there would be fewer plazas, and I'm not sure a plaza would be definable in each city, in each country, the way a street segment tends to be able to be.
That's true. Thank you.
Okay. Yeah, we've got. Okay, Elizabeth, please go ahead.
Yes, first of all, thank you to the speakers. I'm impressed with the presentations, and I've been listening to many webinars of underground urbanism, but every time it blows my mind because there is all the different aspects that are added to it. So I have several questions, but with regards to the Flanders situation, I was wondering so far what you think are the key. Where do you see the key opportunities and challenges in Flanders for climate responsiveness? And maybe both. I mean, I know it's very dense and well built, and very sprawled actually, Flanders area. So that's probably a challenge in itself. That there's few open spaces. So yeah, to hear.
It's to relate it to climate changes. Quite difficult because there's still so much to do with regards to the subsurface and the fact that designers and planners don't recognize it as a valuable dimension, and if they do, it's not sustainable and doesn't add to relevant climate actions. So it's very, very difficult. That's why we're still at the beginning of our policy progress, and actually because the subsurface it's intertwined with so many different policy areas. It's right now I'm looking at it from an urban planning perspective, but in addition, you do have climate and you do have heritage, for instance, and it's I find it very, very challenging to stay on top of it and try to find possible way-ins to make sure that we can increase our quality of life in a broad perspective or a broad way. I hope this kind of answers your question. We still have a lot of work to do.
Yes, yeah, okay. Yeah, I was just curious to see, but because I never heard about I mean, that there is worked on this area already in Flanders. I mean, it's still a new topic for many.
We've only been working on it for about 3 years, and it's parallel to current policy plans such as the new urban policy plan. That's been quite difficult to get through the politics. So it's still low key, but we're working on it, and we're trying to find ways to make it more visible. Yeah.
And I link another question, but that's for the three. So I noticed too, you all work on different depths. So I think with Shana's presentation we were talking about 13 or 15 meters underground when you look at the cross section, I think. Michael working on streets was also wondering how deep do you go? Depends on the goal, on what you try to get out of it. And the last one is 50 to 100 meters to look at the impact of climate underground. So yes, I just wanted to know a reflection on that, because these depths must be linked to certain logic. Maybe Michael?
Yeah, I could start. The 0 to 15, so it's not entirely arbitrary, but I think we were looking, so the 0 to 15, at least in the Swiss context, was looking at basically an initial level in which most property owners would be concerned, and in which we would be within a domain of private property ownership, because I think in Switzerland it's a kind of practical use of 6 meters or something like that, in which someone still has the right, I think, to their what happens beneath their property. And then below that, it becomes public domain. So we didn't really cut it off at the 6 meter point, because we knew for other countries it could vary what that depth means. And in some countries it's, I don't know, even to the center of the earth, although in practical terms, that's always a little bit difficult to plan with. So yeah, I would say, but it's also I would say the depth also depends on what information we have at that depth. So it's only significant if we know what's happening at a particular depth.
I was going to also say, obviously, with regards to, I was looking at the three presentations as a whole, and I think one of the key things that, obviously, looking at the three different presenters, we have an urban designer, we have an architect, and we have an engineer, which pretty much represents the way, 𝐒𝐞𝐬𝐬𝐢𝐨𝐧, basically the way we drive the concept and idea of underground space. So it's a kind of like a multidisciplinary, multisectoral approach to not just planning, conception, developing policy frameworks and all the requirements for underground space. My question here, I'm looking at this from the context of how from a policy framework, how much of integration have we had, in terms of our different works and the biggest challenges we've had in terms of integrating other professional thinking in coming to some of our resolutions. I know we've had different examples of how we've had to work, with different teams. But I think it's one of the key things that outcomes I would like to find out from, anyone that can, maybe the biggest challenges they've had from, maybe even talk about, I know Shana is looking at the policy framework. Maybe you can just advise us on how you're managing this, from a kind of like multi-sectoral, professional point of view.
Okay, so that actually links quite well to our recent new policy project, the Flemish strategy on sustainable development, since it's actually it encompasses the entire Flemish policy, so the administration and the government. It allows us to create a very broad network of all the different disciplines, and key to this transition approach is, we call it several multis. So we have a multi-actor, multidisciplinary approach, multi-temporal, and we're trying to find ways to gather these different disciplines that engage in the subsurface and overcome our we have a language barrier, which is very different, a terminology barrier.
Okay.
That was what I was talking about when we talked to geologists, urban planners. They don't really understand all the characteristics of the subsoil, and they don't know how it affects urban design. And that's a very difficult one, but it goes both ways, and it's not just between geologists and planners. It goes much further than that. So what we're trying to do is, first we're trying to make sense of everybody's different perspective, and then find some kind of common goal, some kind of transition agenda that we can work on. And then eventually, because we're not there yet, the goal is to work with some kind of experiments within that network, and find out how each sector fits in. It's again, it's very difficult just because everybody has its own view on the situation. But that's something that you can see worldwide, and I think every
Absolutely,
city or country is just trying to manage it in different ways. And I'm now fortunate that we have this Flemish policy project, because it allows us to step forward and really ask for cooperation, because the entire Flemish government has agreed that we should. So it has more pull that way than if just some small department says we're trying to work on urban underground planning.
Thank you, and thank you for that, Shana. And yeah, that's well said there. We've been advised that we can go over time, but as well, I would like to also respect every other person's time. So I'm not going to take too much of liberty. But there's a question from Michael. This question is to Asal. How do you think a city could manage shallow geothermal systems, would maintaining the balance require some kind of neighborhood level monitoring?
Yeah, thank you, Michael. Very good question. So how we design geothermal systems, shallow geothermal systems today is based on, as I said, first in, first serve, and very individual. There is no system in place, and most of the designers and installers assume a constant temperature that doesn't change by time, doesn't change by location. And you can imagine that if your ground is, for example, 30, but you assume that it is 21, how that will affect your capacity for heating and cooling. So what my ideal scenario and what I think that eventually should happen for us to be able to use that energy effectively is that, first of all, we have to have a shallow geothermal map. And this is not only based on the geothermal gradient, it's based on all the activities above and beyond, above and underground that actually contributes to temperature change in shallow subsurface, like infrastructures, like anything that can be considered as a heat source or heat sinks. But once we have this geothermal map for cities, then we can match the demand with the opportunity. So then we can identify the large consumers and hopefully match them with a large potential of energy, thermal energy right underneath or within the close proximity of them. So once we do that, automatically the balance will be there, because you have a hospital which requires more cooling, for example, but then you have a high rise that no matter what requires hot water. So there is always a balance if you look at it in a holistic view of that the whole urban area should be actually switching to geothermal, because we do have that capacity to fulfill the demand. So that's my ideal scenario. When that happens, I have no idea, but yeah, we'll push for it.
Thank you.
Oh, really interesting. And there's a question I always ask, especially professionals that are tasked with the mandate of developing a policy for the underground space, building a framework for integration of underground space, adopting technology to how we elucidate or how we capture data information from the underground space. Um, Different cities, especially, look at the developed, most of the developed cities in the world. Is there, any understanding from city by city with regards to the ratio of the footprint of the underground space that is used? So I'll give an example. So for the example, in the UK, there are projects ongoing to kind of like map the underground space, and it will be very beneficial from a value proposition point of view to understand from a footprint point of view what actually is the ratio of underground space use that we're currently using. Because the idea of the underground space is basically to increase that value of a square, um, of a meter square. So you're optimizing it. There's the existing resource there. You understand what the resource requirements are, and you're also optimizing the value of that. So I'm just saying this is just me thinking out loud in terms of some of the questions I've asked professionals, and I'll continue to ask, and that draws me as well to Asal. I would like to ask this question. So in a city where um you have thousands of boreholes, existing boreholes, is there any benefit in terms of integrating? Because with regards to how this geothermal energy stuff works, I'm just curious to know, will there be any opportunities in such cities where you have quite a significant amount of boreholes, and possibility of integrating um, opportunities to explore um, geothermal energies, from some of these assets, and some of them, because of the volume of the boreholes, really do have impacts. They do impact kind of like the geostructures of the cities as well.
Well, yeah, absolutely, yes. Because we can turn a borehole to a borehole heat exchanger. We just embed pipes with water circulating within closed loop in there, and I assume that these boreholes are observation wells. Is that right?
Yeah,
Most of them.
to be fair,
Yeah.
some of them can be observation wells and some of them can actually be boreholes where you're drawing water from.
Yeah, it can certainly be used. And the borehole, that if we do it properly, we actually, for the borehole heat exchanger, the borehole has got a very small diameter. We're talking about less than 150 millimeter in diameter, because it's
Yep.
only drilled for the purpose of heat exchanger. And we usually put the pipes in there, and then we grout it, because we actually, the grout usually facilitates and improves the heat exchange between the soil and the water inside the borehole. But that's an ideal scenario, but still we cannot afford it because it's very expensive to drill those boreholes, even for the individual house. If the boreholes are there, if the boreholes are available, there is certainly a way to make them a borehole heat exchangers. And yeah, absolutely, yes.
Interesting, really very interesting. Okay. If in the absence of any other question, I'm just going to check to see. Oh yes, we do have questions here. So all right, cool. All right, so Mike, so see this is Shannon. I'm very happy to send you, okay, on the line. Okay, so
It's a response to his question.
okay.
That was
Thank you,
very
Shana.
don't
Thank
worry.
you.
Okay. All right. So thank you very much once again, everyone. I believe this is a good place to actually round this off. It's a good thing that this is recorded. I'll be looking forward to, listening back to this and sharing it with my network as well. I'm pretty sure the ITACUS network will be, would benefit greatly from this. Thank you very much once again. Shana, Michael, and Asal, and to our hosts, Elrine and Elizabeth. Thank you very much for having us. It's been an absolute pleasure.
Yes, thank you very much. And I want to mention that we have a virtual urban cafe starting in 15 minutes. Yeah, this is informal. You can talk about different topics. And it's moderated by Patricia Canelas. She's from Oxford University, teaching in sustainable development. So you're welcome all there.
Thank you very much, Elizabeth. Thank you very much once again, everyone.
Thank you very much.
Thank you.
Have a good
Thank you.
evening.
Thank
Bye.
you.